There's Chapter 1, Lesson 7, which is about functions, and in Lesson 6 we talked about relations. And a relation was defined as a relationship between two numbers. Now, when we talk about functions, we're talking about a special kind of relationship. Think about everyone you know. You have a relationship with everyone you know. They're your friends, your aunt, your uncle, your parents, your grandparents, cousins, brothers, sisters, everything. You have a different relationship with everyone. Well, a function is a special relationship. So the function would be like the relationship that you have with your boyfriend or girlfriend or husband or wife. It's a very special relationship. There's exactly one output for each input. So let's define that. A function is a special relation with only one output for each input. Okay, so that means that if we plug in a domain element, so for example, let's say we plug in 2, we can only get one answer out. We can't get 2 answers out. So when we look at a function graphically, actually let's start with a mapping. Okay, well, remember from our last lesson, when we have a mapping, we have our x and our y's, and I'm just going to do a really simple one. Okay, then we draw our arrows that represent our relationship. Okay, this is our domain, this is our range, and as you can see, every input only gives us one output. Now, that means that this is a function. If I do another example with another set of x's and y's, now I can have 2 different x's go to the same y, and that's okay because each of these inputs is only giving me one output. Again, here's my domain, and here's my range, and this is a function. What happens when I'm getting into the area of not a function? I'll show you an example of not a function. If I have some number giving me 2 outputs, this is not a function. Okay, so every x can only go to one y, so 1 arrow each coming off of the x's. Because I had 2 arrows coming off of this x, that is what made this not a function. So you can't have an x with 2 different y's. You can have a y with 2 different x's, that's okay, but you cannot have an x with 2 different y's. Okay, so on a map or on a graph, we'll talk about a vertical line test shortly. That's a pictorial representation, but for right now, we're going to determine if each relation is a function or not. Okay, and I'm going to go ahead and pause this while I write out the 3 different relations that we're going to check. Okay, so here are the three examples that we're going to determine if these relations are functions or not. Oops, I forgot to draw the arrows. Okay, so looking at this, I have one arrow each on the x's. So A is a yes. This is a function. B, I have 1 to 4, 3 to 2, 5 to 4, and 1 to negative 4. Here I have the same x going to two different y's. So no, this is not a function. Now, if you need to draw a mapping to draw the arrows, we can do that quickly. I have a 1, 3, 5, and then a 1 repeats, which we don't write the same number twice. And then I have a 4, a 2, a 4, and a negative 4. 1 goes to 4, 3 goes to 2, 5 goes to 4, and 1 goes to negative 4. And right here, because I have two arrows, that's what tells me it is not a function. And my last example, I have a set of ordered pairs, 2 to 1, 3 to negative 2, 3 to 1, and then 2 to negative 2. So I have two sets, the 2 to 1 and 2 to negative 2, and then the 3 to negative 2 and the 3 to 1, that are telling me absolutely no, this is not a function. Let's look at some other types of functions. We can have a discrete function, or we can have a continuous function. Okay, discrete functions occur when we have individual points. And continuous functions occur when we are graphed with a line or curve. And that should be a smooth curve, not a zigzaggy curve. Okay, individual points. These are if we try to figure out something that is discrete versus continuous. If you're discrete, your values are not running into each other. Okay, for example, pizzas. I can have one pizza, I can have 1.5 pizzas, I can have 2 pizzas, I can have 3 1/4 pizzas. But I can't have 1.2683956 pizzas. My values aren't going to run into each other. So between the fractions, I'm not going to have more fractions. Continuous happens when your values blend or bleed into each other. So as an example for continuous, growing. We gradually grow. So one day you're 5 foot, the next day you're just a little over, and you keep going until you're finally 5'1". And you grow some more until you're 5'2", but you don't instantly wake up the next day exactly 1 inch taller. Other examples of discrete is anything that can be represented by an integer, so the number of people in a classroom. We can't have parts of people bleeding into each other. We have individual people. Okay, so that's discrete versus continuous, and they can both be functions. We can have discrete functions and we can have continuous functions. Okay, so let's draw a graph. And there's an ice sculpting competition. Okay, look, there should have been an at there. At an ice sculpting competition, each sculpture's height was measured to make sure it was within the regulated height range. Of 0 to 6 feet, although I don't know how you would have a 0-foot ice sculpture. Okay, the measurements were as follows. Okay, team 1, 4 feet. Team 2, 4.5 feet. Team 3, 3.2 feet. Team 4, 5.1 feet. And Team 5, 4.8 feet. Okay, I'm going to move this up a little. We're asked to make a table showing the values or showing the relation. Then we are asked to determine domain and range. Then we are asked to graph it. And finally, state whether it is discrete or continuous. Okay, so the first thing we're going to do is make a table, and I'm going to make my table sideways this time because it takes up less room that way. So team 1 was 4 feet, team 2 was 4.5, team 3 was 3.2, team 4 was 5.1, and team 5 was 4.8. Okay. My domain is the set 1, 2, 3, 4, and 5. Those are my x values. And my range is the heights 4, 4.5, 3.2, 5.1, and 4.8. Next, we are asked to graph it. And before we graph it, we are asked to list it in a set of ordered pairs. So I'm going to go ahead and write out my ordered pairs. And since I am graphing decimals, I'm going to set my scale a little differently than I might normally. Instead of going up by ones, I'm going to go up by halves, which will give me sort of a better gauge for graphing some of these. So I'm going to make my y-axis, and my tallest one is 5.1, so I'm going to make my tallest point 5.5, 5, 4.5, 4, 3.5, 3, 2.5, 2, 1.5, 1, 1/2, 0, and then my x-axis are just integers, so that shouldn't be too bad. My first point is 1, 4, my first height. My next height is 2, 4.5. Then I have 3, 3.2, which is kind of halfway between 3 and 3.5. Then I have 4, 5.1, which is just above 5, and then 5, 4.8, which is just below 5. And again, if I did this on graph paper, it would work out so much better. And finally, D, we were asked to state if this was discrete or continuous and to state why. This is a discrete function because our sculptures are not running into each other. Everybody is making an individual sculpture. We're not making like I sculpt part and you sculpt part and they sculpt part of some big whole. We're making individual sculptures, so this is a discrete function. Let's look at another example of kind of the same idea. We have a bird feeder. We'll hold up to 3 quarts of seed. Again, these problems are coming straight out of the book, so if you're having a hard time reading my writing, just open up the page in the book. Okay. The feeder weighs 2.3 pounds when empty and 13.4 pounds when full. Okay, so we're asked to make a table at 0, 1, 2, and 3 quarts, weighing 2.3, 6, 9.7, and 13.4 pounds, respectively. And then we are asked to determine the domain and range. We are asked to graph it, again, and make a set of ordered pairs. And then we are asked to tell if it is discrete or continuous. So the first thing we're going to do is make our table. So I have 0 quarts, 1 quart, 2 quarts, and 3 quarts. And that's 2.3 pounds, 6 pounds, 9.7 pounds, and 13.4 pounds. My domain is 0, 1, 2, and 3. My range is 2.3, 6, 9.7, and 13.4. I'm going to graph this. And I am not sure I have enough room. Let me slide that a little bit more. Okay, so I have to go between 2 and 13 and a half. So I'm going to stick with my going by halves. 13, 12 and a half, 12, 11 and a half, 11, 10 and a half, 10, 9 and a half, 9, 8 and a half, 8, 7 and a half, 7, 6 and a half, 6, 5 and a half, 5, 4 and a half, 4. Need a little bit more room. 3 and a half, 3, 2 and a half, 2. And then I'm just going to cut across here and have 1, 2, and 3. Okay, at 0, I'm at 2.3 pounds, which is just under 2.5. At 1, I am at 6 pounds. At 2, I am at 9.7, so it's about halfway between 9.5 and 10. And at 3, I am at 13.4, which is just under 13.5. And is this discrete or continuous? If the birds are eating the seed, the weight is going to gradually decrease If I'm filling up the bird feeder, the weight is going to gradually increase because of all the little individual seeds that are going to fill it up. So there are going to be times when it is in between these weights. So we're going to graph this with a line, and that is a continuous function because there are times when the weight is between as the volume. So those are going to adjust. I'm not going to have 1 quart this second and then like some bird's going to come suck up a whole quart. It's going to gradually decrease. So that is a continuous function. All right, the next thing I want to talk about is the vertical line test. Okay, and the vertical line test can be used to determine if a graph is a function or not. Okay, and this is how it works. A vertical line will only touch a function in one place. So, let me show you an example of that. Just give you 2 coordinate pairs. Or sorry, 2 coordinate planes, not pairs. And if I draw a parabola, or if I draw a circle, a vertical line coming down through the graph will only touch a function in one place. If I touch in more than one place, I am not a function. So as you can see here, I'm only touching the graph in 1 point, whereas here I'm touching in 2 points. Therefore, this circle is not a function, but this parabola is a function. There's another example in the book, and that is where we have a graph that looks like this. 1 point has a colored in dot. Directly underneath that somewhere or above that somewhere we have an open dot. This represents the fact that this is only touching in 1 point. This is not a point. So this is still a function. So be aware of that. Otherwise, unless there's an open circle and it touches in 2 places, it's not a function. So let's look at some examples. We're going to determine if negative 3x plus y equals 8 is a function. Okay, so we're going to graph this. And to graph it, we're going to make a set of tables. Sorry, a table of ordered pairs. And if we haven't done this before, do a quick and easy method. I'm going to pick random values for x. I usually start with 0. And so I plug in 0 for x and find out what y equals. And in this case, that means y equals 8. And then I plug in another number for x. So negative 3 plus y equals 8. So what minus 3 is equal to 8? That would be 11. I'm going to do a negative 1. So I have 3 plus y equals 8. So that would make y 5. Now, I need at least 3 points to make my graph. And I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, because I go up to 11. And so my first point is 0, 8. I have 1, 11. And I have negative 1, 5. Now the reason I said you want 3 points is because when we graph this on actual graph paper and we use a ruler, the points should all line up on a straight line. If they don't line up on a straight line, then you know you've graphed a point wrong. We'll just pretend that this is a straight line. Will it pass the vertical line test? Well, if I come in and I draw a vertical line at any given point, it will only touch once. So yes, it is a function. Okay, and next we'll go on to the finding function values section of this chapter. Okay, finding function values. All right, so first we want to talk about what is function notation. If we have an equation, y equals 3x plus 6, in function notation, we replace the y with f of x. And what this tells us, it tells us the equation is a function and that x is the domain. So when we're asked to find each value from function notation, if I'm given f of x is equal to negative 4x plus 7 and I want to find f of 2, what I do is I plug in a 2 where the x was. So see that x gets replaced with the 2. I multiply negative 8 plus 7, so f of 2 is equal to negative 1. Or if I have f of negative 3 plus 1, what I do is I take the f part, and so f of negative 3 is negative 4 times negative 3 plus 7. So that is this portion. And then I add a plus 1 on the end because it was hanging out outside here. So I have 12 plus 7 plus 1, and that gives me 20. So f of negative 3 plus 1 is equal to 20. Let's try a couple more. Given that f of x is equal to 2x minus 3, I'm going to find f of 1. That is going to be 2 times 1 minus 3, which is 2 minus 3, which is negative 1. Or I can find 6 minus f of 5. That is going to be 6 minus, let me do bracket on that. F of 5 is 2 times 5 minus 3. So that's 6 minus 10 minus 3. So that's 6 minus 7. So that's negative 1 also. F of negative 2, I'm going to replace the x with a negative 2. So that's negative 4 minus 3, which gives me negative 7. And then f of negative 1 plus f of 2. So the first thing I need to do is replace the x with negative 1. And then to add to that, I replace the x with 2. So I have negative 2 minus 3 plus 4 minus 3, negative 5 plus 1 gives me negative 4. We can also have functions that are not a straight line. These are called nonlinear functions. It's the same idea, we're just going to have some exponents in there. Oh, they're using H, sorry. We can use other letters. Usually we use F, G, and H, but any letter can be used. So here they've got h of t is equal to negative 16t squared plus 68t plus 2. And we want to find h of 4. So if I plug in 4, I have negative 16 times 16, because I need to do that exponent first. And then multiplication, 68 times 4 is 272 plus 2. And then 16 times 16 gives me negative 256 plus 272 plus 2. And then when I add those together, I get 16 plus 2, which gives me 18. If I do another example, this one is called a compound. Well, no, it's not. Sorry, I lied. It's not a compound. What I want to do with this is I'm going to replace t with g. And then I'm going to multiply the whole thing by 2. So, I'm going to have 2 times negative 16 g squared plus 68g plus 2. So I just took the t out and I put the g in, and then I need to distribute this 2 to everything. And that gives me negative 32g squared plus 68 times 2 is 136g plus 4. Okay, let's try just a couple more. We're going to use the same equation for all of these. Okay, so C, we're going to find f of 4. So I plug in 4 for t, so that's 2 times 4 to the third. 4 to the third is 64, so that's 2 times 64. And 64 times 2 is 128. D is f of negative 5. So I plug in negative 5 to the third. Now negative 5 to the third is negative 5 times negative 5 times negative 5. I have 3 negatives, which is going to give me a negative number. So that's 2 times negative 125. And 2 times negative 125 is negative 250. Now we're going to get a little bit more complicated with this next one. I have 3 times f of t plus 2. So what that's telling me is I'm going to replace all of the x's with t's. I'm going to multiply it by 3, and then I'm going to add 2 to it. So I don't know why I put an x there. There's no x's. So I'm just going to multiply by 3 and add 2 because the t is already in there. So this is going to be 6t to the third plus 2. And finally, our last example, f of negative 3 minus f of 1. So f of negative 3 is replacing the t with a negative 3, and then I'm going to subtract 2 times 1 to the third. So I need to do my exponents first. So this is 2 times negative 27 because I have 3 negatives being multiplied together, minus 2 times 1. So I have negative 54 minus 2, which gives me a negative 56. And now we're going to just go over the note taking, and that'll be the end of lesson 7. Okay, note taking for chapter 1, lesson 7, and we want to look at 2 things that we'll expect to learn. We're going to determine whether a relation is a function or not, and we are going to find function values. Okay, review vocabulary. We're going to define reciprocals in our own words, so my definition might be a little different than yours, but a reciprocal, reciprocals are upside down from one another. And I'm going to do an example. 2/3 and 3/2. Okay, that's just my version. Your wording might be a little different. Okay, now let's look at new vocabulary. All right. A graph that consists of points that are not connected is a blank. All right, so if the points are not connected, that is a discrete function or graph. A blank is a function graphed with a line or smooth curve. Now these are being connected, the dots are being connected, so that is a continuous function. A blank is a relationship between input and output. Well, that would be a function. It can actually technically also be a relation from our previous lesson. So if you wrote relation, you're pretty close. A test used to determine whether or not a graph represents a function is known as the vertical line test. Okay, and that's where we can draw a vertical line straight up and down, and we would only touch the graph once. If we only touch the graph once, we are a function. If we touch the graph more than once, it is not a function. And speaking of function, I need to look up the definition of a function. So I've got my handy dandy Webster's dictionary here. I went too far. Okay, function. Right. Well, there's a lot of different definitions of functions, so let me look here. The normal or characteristic action of anything, special duty or performance required in the course of work. Here we go. A thing that depends on and varies with something else. Okay, that is a good English definition because the very next definition in the dictionary is the math definition, which says a quantity whose value depends on that of another quantity. A thing that depends on and varies with something else. That is the definition of a function in English, and it highly aligns to the definition of a function in math. And how this can help us to remember is one value depends on the other. Okay, so let's look at the next page. We have some examples here. Fill in each blank to tell how to determine if a relation is a function. Okay, look at the table to see if each member of the domain, remember this is our domain and this is our range, corresponds to only one member of the range. Okay, here I have 1 going to -2 and I have 1 going to 5. They didn't ask us this, but we're going to go ahead and answer it. Not a function. 2, use the vertical line test. If no vertical line can be drawn so that it intersects the graph more than once, it is a function. Look at this. When I draw a vertical line, I intersect twice. Not a function. All right, here we're going to find function values. F of 3 means we're going to plug in 3. So I have 21 minus 4, and 21 minus 4 is 17. I plug in -2, and so I have -14 minus 4 giving me a -18. I plug in 0. 0 minus 4 is -4, and I plug in -3. -21 minus 4 is -25. So that's how we find function values. And last but not least, a student who is trying to help a friend remember how functions are different from relations and that are not functions, gave the following advice. Just remember that functions are very strict and never give you a choice. Explain how this might help you to remember what a function is. Okay, functions are very strict and never give you a choice. What that means is for every input, there is only one output. No choice to have more than one output, or something similar.